you. Thank you very much. I'm very excited to have the opportunity to present my results here. So I'm going to be talking mostly about this paper that came out in the archive very recently, although there are here 3 other contributions that are related to it that I'll explain potentially. So the work that I want to talk about is, it falls under the umbrella of this general idea that I'm very excited about in the last year. So actually, I did a sabbatical here in Ireland, and this got me thinking about many of the ideas, and they are generally related to how you get the statistics of continuously monitored quantum systems. So a quantum system, a typical example of a continuous measurement is a cavity where you monitor the photons that they leak out, or as Letitia just put it, like monitoring, say, the dynamics of the quantum dot system. Now, this has a strong analogy with the idea of a hidden Markov model, where you don't see the system, you never see the quantum system, so it's kind of like the hidden layer in the Markov model. What you see is essentially just a measurement record, right? So what you want to do is you want to say as much as possible about this hidden layer from the visible layer that you see. And there are many questions that you can ask, which have many exciting things associated to them, and they were already discussed in this talk. So for example, you could ask the question, what is the time between 2 quantum jumps? You could ask about current correlation functions, or you could go to the school counting statistics and histogram your detection records, and so on, right? And there are also many interesting applications that I'm particularly looking into. First of all, this is already a nice tool for just learning about your quantum system, right? Like, in optics, people study the G2 function or what else. This is exactly, this falls under this category. But of course, you can do metrology like Marco showed. You can do timekeeping like Michael showed. We've been looking also a little bit in time result thermodynamics, like Letitia showed. So there are many interesting applications. So this slide is a little bit redundant because this has been presented quite a few times before, but let me just quickly go to the notation that I'm using. I'm just going to assume a Lindblad-Messer equation with different jump channels. The channels that I usually have in mind is something like a system of, let's say, dots or spin chain, where you can have different kinds of mechanisms. So in this example, you can, for example, inject an excitation in the left, or extract it in the left, inject in the right, extract in the right. So this would be a system with 4 jump channels. And so essentially, in the quantum jump unraveling, the dynamics goes like this. At each time step, you sample a probability to decide if you're going to jump or not. If you jump, then you update your state. Otherwise, you evolve your system according to this no-jump superoperator that is essentially subtracting from the Lagrangian the jump part. And so at each time step, you essentially have a random number, dnk, which is going to be 0 if, which is going to be 1 if a jump occurs in channel K. And so in your quantum trajectory, right, the data that you get is essentially the sequence of dnks for each time step. That is the measurement record. Or if you want to write it in a slightly more organized way, it is a sequence of, like Yoshihiko presented, a sequence of channels and times, right? So, and this is an interesting stochastic process from the perspective of stochastic processes, in part because tau is a continuous parameter, but k runs over a finite alphabet of symbols. So your stochastic process mixes this finiteness of the alphabet with this continuous motion. So the thing I'm going to be talking a lot about here is how to build currents out of this. So I will define a current in general, or more precisely the charge, which is the integrated current, as just an integral of these increments. So this is a stochastic variable, right, for a given process. And it's a weighted sum of these dnk with these quantities nu k, where these nu k are just numbers or weights that depend on the kind of physics that you're interested in. So, for example, if you want to just count jumps, right, just you don't care about which channel they occur, you just want to count them, you can just choose this nu k to be all equal 1, and this will give you the dynamic connectivity. But if you have some physical meaning to these jumps, such as in this example, where some jumps mean injection and some jumps mean extraction, you could, for example, define an excitation current. And you can set one of the news to 1 and one to -1, and this will then tell you, this n can then go up and down, and this would be giving you how many excitations have entered or left the system. So this is a nice kind of way of building these currents depending on the physics that you're interested in. Okay, so the problem that I want to talk about is first passage time for this kind of process. Now, first passage time, it can be phrased as follows. You have some kind of stochastic process, and you have some event, right? And you want to say when is the first time that this event occurs, right? So if you have a person with a martini here walking around, and you define the event as falling down a cliff or climbing a bar, then eventually what you want to do is you have this x of t, and you say when is the first time in which this event occurs. For me, here, I'm going to focus on an event which is leaving a certain region. So the system starts in a region of space. X of t is just a generic stochastic process for now. I'll explain more what it means in our case. But for now, X is just a stochastic process, and it starts inside a certain region, R, and I'm going to ask what is the first time that X leaves this region. Now, you might think that this should be related to the probability of finding X inside the region that you want. But this is actually quite subtle. This object here does not give you any first passage time, because in the past, the system might have left the region and then come back. So this object just tells you what's the probability that at a given time the system is in that region. So it doesn't say anything about whether it left or not the region before. So one way to do first passage time problems, which is very useful, is through this idea of absorbing boundary conditions. Usually you will have some kind of equation, evolution equation for your probabilities, a master equation, whatever. And you can just say, look, I force that my px of t is 0 for every x outside of my interval. So I just impose that by hand. And when I do that, this is going to give me a new dynamical equation, a new evolution, right? Because I'm imposing this boundary condition, which I'm going to call PR. So this R here, which I'm going to kind of carry out for the entire talk, is just to emphasize that this is a new dynamics, right? When you impose absorbing boundaries, you generate a new type of dynamics. And this, because you're imposing that this P of X is 0 outside of your region, that probability is no longer conserved. You're losing probability, right? Because whenever the system leaves that region, you kill the probability. And so if you just integrate your probability that you're left, then you get an actual survival probability, which is the probability that after a time t, the system is still within that region. And then from this, you can get the first passage time distribution as a derivative of the survival probability. And this is because, the logic behind this equation is just because the first passage time distribution is essentially the probability that the system is inside the region at a given time t minus the probability that it is not. So essentially the probability that it was inside at time t and then left at time t. And if it happens that your survival probability is 0 and infinity, then it means that the boundary is always reached. This doesn't always have to be. Sometimes you can have problems where the boundary, there's a finite probability that you never reach your boundary. And if that's not the case, then your PT distribution will not be normalized. So this is just something to keep in mind. So now I want to try to talk about first passage time for quantum systems. So first of all, I want to argue that one could ask, what is the first passage time for a quantum system to do something? And I want to argue that that question doesn't even make sense, because a quantum system, it's not in a specific state. It lives in different positions. So the idea of defining, an event for a quantum system is still defined. But for the classical measurement record, it's absolutely fine. So here I want to talk about the first passage time that your measurement record achieves some kind of threshold or leaves some kind of region. In particular, I'm going to look first for quantum jumps, and I'm going to look at the charge, at the accumulated charge, and I'm going to ask exactly this question. When is the first time that my next charge leaves a certain region? So it starts at 0, you're counting events with some weights. It can be positive or negative, and you ask what's the first time that it leaves a certain region. So our approach is going to be based on this charge resolved state. So you have rho C, which is the conditional stochastic state of the system, and you can define a charge resolved state, which is just the ensemble average of this times a Kronecker delta that your random variable n of t has a certain value n. Right? So you're essentially filtering out of all stochastic evolutions, those evolutions that have exactly n, big N equal little n at any given time. And this object is such that if you take the trace of this density matrix, you get the full counting statistics probability, right? So it's encoding the probability in its normalization. So one of the nice things about this charge resolved state is that it satisfies a charge resolved master equation. So and this equation has kind of an intuitive interpretation. Essentially, the rate of change at which rho n, the rate of change of rho n is related to a no jump term, L0, with the same rho n, and a kind of density matrix flow. It's not really a probability flow, it's kind of a flow of density matrix from the other n's associated to the jumps, right? Because Lk changes my n by a certain number nu k, and so this has a flow of density matrix from the other rho n. So yeah, so the nice thing about this equation is that now once you have this, it is absolutely immediate to apply absorbing boundary conditions. Right? You just force your rows to be 0 for any little n that is not in your region of interest. Right? So you just eliminate whatever density matrix outside of this region. And this will give you rise now to a new evolution. Again, I'm going to put an R here, just be careful, rho and R, which is conditioned on this specific region R. And if you normalize this, you get your probability. And from this, you get your survival probability, and you get your first passage time probability. So all of the results that I showed before now really apply. Okay, so just to give you an example, suppose you have a system with one injection and one extraction channel, and you choose your weights to be plus or minus, so you're looking at some kind of excitation current. Then your charge result equation will have a term connecting rho n to rho n minus 1 and rho n to rho n plus 1. You can write this in an organized kind of matrix form. And this is a kind of matrix of super operators, but you know the idea is valid. So essentially, you just have a vector, which a vector of density matrices going from A to B, your region of interest. And then essentially it's just a coupled system of equations, right? And one of the nice things that we can show is that the first passage time distribution is given by the upward jumps in the rightmost boundary and the lowering jumps in the leftmost boundary. Now, as we've seen here in other talks, these kinds of terms represent dynamical activities, right? So this gives a nice interpretation of your first passage time as essentially the activities at the boundaries of your region, right? So you lose probability because you have density matrices kind of leaving your boundary, and essentially the dynamical activity at these boundaries is what defines your first passage time distribution. Okay, so here's an example to kind of clarify. Suppose you have a qubit with a Rabi drive, and so omega is the intensity of the Rabi drive, and it's also finite temperature, so there's a damping rate gamma and a temperature, Bose-Einstein temperature n bar. And suppose we choose boundaries -5 and 5. Now, if you do this with quantum trajectories, here's how it's going to look like. Each curve here is an individual quantum trajectory. And if you want to obtain your first passage time distribution, suppose you want to talk about what is the probability that the first passage time is 10. And you need to look at all trajectories that cross this region, the +5 and -5, before 10, right? And then you make a histogram. So you can histogram your trajectories, and you would obtain your FPT distribution. But of course, this is very expensive, right? I mean, doing these quantum trajectories is extremely expensive, and it's not really practical to keep on doing. So with our method, what is very nice is that you get a deterministic equation, right? So for this, and so this is an example. So here's the probability that you find a system in given n's, the survival, and the first passage time. So you see that when it starts, the probability starts high. You can clearly see that you're losing probability because you have these absorbing boundaries, and so the probability is leaving your system. And so your survival probability goes down, and you have to take the derivative of this to get the first passage time distribution. That is kind of the idea. One of the things that we can use our model to try to gain some insight is into the kinetic uncertainty relations. So TiQT just presented TURs and KURs for various observables, which appear in full complex statistics. There's also variations of these bounds for first passage times. So in 2017, Garahan showed that the signal-to-noise ratio of the first passage time, so the average first passage time divided by its variance, is bounded by the dynamical activity in the steady state. So, and this is quite similar to one of the bounds that TiQT presented, but here recast in terms of the first passage time. And so essentially what you get is that, again, fluctuations in first passage time are related to activity. That's what this bound means. But this bound is classical. It only holds for incoherent master equations or classical stochastic processes, and so it can be violated in the quantum regime. More recently, Van Vu and Saito showed that there's a correction to this, where the signal-to-noise ratio has still the same term associated to the dynamical activity, plus a correction, Q. Just to give some reference, for the qubit model we were discussing, these are the explicit expressions, and just it's important to notice that this Q is proportional to the Rabi drive. So the Rabi drive is what makes the process coherent. If you kill it, you get a classical stochastic process where the qubit just jumps up and down, and so qubit 0. So this is what you get. And for formalism, it's very easy to now simulate these quantities for arbitrary parameters and so on. So this is just a plot to illustrate what is happening. This is the Rabi drive intensity on the horizontal axis. Left is cold temperatures, right is a hot temperature, so by playing with the n bar. And so you see that at cold temperatures, the the classical bound can actually be violated. You see that because the signal-to-noise ratio in black goes above the classical bound, which is red. So it's small, the violation. It's not big, but it can be violated as expected. But overall, the classical bound follows kind of closely the evolution of signal-to-noise ratio. The quantum bound, on the other hand, is never violated, right? So and that's for sure, it cannot, right? So the blue will never be below black. However, it is also quite loose, and it doesn't seem to describe very well the behavior of the SNR, right? So you have this kind of trade-off. Of course, this is highly model-dependent, right? This is not at all a general conclusion, but it's interesting to see, how do the bounds behave compared to the actual quantity that you want to compute. And these quantities are notoriously hard to compute using quantum trajectories, so this offers a nice way of studying it. Another semi-obvious application of this, which I would be remiss not to mention, is for timekeeping. So we've already seen in this conference before that when you describe quantum jumps, you can use this in two ensembles. You can assume that the number of jumps is fixed, and so the final time of the process can fluctuate, or you can assume that the final time of the process is fixed, and therefore the number of jumps fluctuates. Of course, if you want to have a clock, then you need to be on this ensemble, because for a clock you can only count events, and if you want to use this as a clock, you cannot really fix your TF, right? You don't know how to fix it. So for a clock, you just need to count how many jumps you have. And so you can define a standard of time by just saying, my time standard is the first passage time when n of t reaches a certain boundary, right? And then your standard of time will depend on your choice of boundary and your choice of current n of t. So just to give an illustration of this, suppose you just take the dynamical activity, so you take all of your new K2B1, and then your charge resolved master equation is going to be essentially rho n only gets a flow from below, right? Because the charges can only go up. And so in this case, your region is essentially 0 to a certain b, right? That's all you need to consider. And the first passage time distribution is just given by the dynamical activity at the boundary here, right? So this b is essentially the region that you want to consider, and it defines essentially your plot, right? So if B is very small, you're going to have a good resolution and a low precision, and if B is very large, then your relative precision will be better, but your resolution is going to go down. So essentially the resolution is determined by how many jumps you want to count. Okay, so moving on, I want to talk now about the diffusive unraveling. I realize I'm going a little bit slow. So for quantum diffusion, the difference is that now the system will evolve according to the stochastic master equation, where the current is now essentially measuring not L dagger L, but this operator X, which is L plus L dagger with phases phi that you're free to adjust. So the current is a weighted average of these XK, and with these dWdt and these, oh, there's a K mixing here, sorry. These dWdt are just the Wiener increments. So in this case, what we showed was that you can still define a charge result master equation, but your little n here, or your current, sorry, is now a continuous stochastic process, right? It's not discrete. And what is nice is that in this case you get what looks like a Fokker-Planck equation. So essentially, the rate of change of your rho n has the usual Lindblad term, and then there's this super operator k, which is essentially a rho plus rho a dagger. It appears as a drift term, so the first derivative of the density matrix. And there's also a diffusion term, which depends only on your choice of mu k. And so this is kind of similar to equations that appear in reaction diffusion systems. Essentially, you have a system that can diffuse, in this case diffusing the variable x, but it also has internal degrees of freedom, so it's a density matrix, right? It's still a state, so it has internal structure. And a kind of similar but Fokker-Planck equation I just want to mention was recently derived in this paper as well, but for a different kind of observable. And I just want to say that this is, once you have this, then it's very easy to implement absorbing boundaries, because again, you just set your rho n to be 0 outside of the region that you want to work with. And so let me illustrate this with an example again for a qubit. Suppose we adjust things such that your variable x is essentially the sigma y operator. And suppose we choose a region to be anywhere from -infinity to a certain threshold. Here there's this slight change of notation where I was calling this little b. Here we're calling n threshold, and we choose it to be 1 just for illustration purposes. So essentially, again, here are the stochastic trajectories. If you histogram in this direction, you get a first passage time distribution. Here we will also show that you can histogram in this direction as well, and this gives you the full counting statistics distribution. And of course, you can now do the same thing for the qubit model. You see that the probability distribution fluctuates, but notice the vertical axis is going down, which means that you're losing probability. You also see nice oscillations here in the first passage time distribution. This is, a consequence of the Rabi oscillations that are reflected in this kind of process. And let me quickly try to finish by just saying that there is a deep connection between what we're doing and the implementation of feedback control. So essentially, in either jumps or diffusion, you have an underlying measurable, detectable stochastic process. For quantum jumps, it's a random variable xj at each time step, which runs over a finite alphabet. For quantum diffusion, it's a continuous stochastic process, but these are detectable things. And what you want to do for first passage times is not too different than what you want to do for feedback. You essentially want to condition your dynamics on this measurement record, right? So in first passage time, you say, well, when this stochastic process reaches some kind of threshold, I stop. And in feedback, you say, well, given this stochastic record, I change something in my Hamiltonian, for example. I modify the Hamiltonian of the system given this stochastic process, right? So doing generic kinds of, in this way, we can do any kind of first passage times and any kind of feedback. And at the level of the master equation, actually implementing this is super easy, right? You can come up with super weird stopping criteria for first passage time. You can say, I'm going to stop when I observe 5 jumps of this type, followed by 3 of this type. You can come up with any kind of criteria you want to write a first passage time problem. But that's always at the level of control trajectories, and that is very expensive to simulate and doesn't give you many insights. So what we tried to do here was write this in a deterministic way, such that you can write equations that describe your process, right? And this is valuable. One famous example is there's a current feedback from Wiseman and Gerard, which you write down a master equation that includes feedback, and it's deterministic, and it gives you a lot of insights into the mechanisms behind feedback. And I just want to mention that our formalism is very trivially extendable to feedback, even though we didn't study this. Suppose you want to change your Hamiltonian to be some h that depends on your charge, and you can also do the same for the jump operators. Then essentially, since these equations are resolved in n, it is very easy to just introduce modify your Hamiltonian to be resolved in n as well. So that is all I had to say. Thank you very much. And I just want to say, so I work also at PRX Quantum, and we have a huge shortage of referees. We need referees, so please referee. Please, we need referees. Thank you very much.
Just a quick question about the feedback. One place that occurs to me where this would be extremely useful is in neuroscience, where in neuroscience models of pre-synaptic and post-synaptic activity, typically the integrated fire model is counting up to some particular number. Then it changes something through some other circuit back in the pre-synaptic level. So this would substantially, there is all kinds of difficulties. But presumably there are quantum versions of that as well. So we can start thinking about quantum spiking perceptrons in this setting, which would be really good.
And is that like continuous time, like Cocker-Flint kind of models, or discrete?
Both. Oh, no, sorry, they're in the neuroscience, they're all continuous time.
Continuous time, okay. Yeah, so this kind of equation, so there is, the known equation for current feedback, where, the mechanism that feeds back to the current. This is feeding back on the charge. There is also another paper that I mentioned before, which feeds back on a filtered current, so current runs through a filter. So there are,
So in the uncertainty of this first passage time, now also relating this somehow to clocks, is there dependence of the uncertainty of the first passage time, a relation between this and the time it takes the whole system to actually exit this region of interest?
I'm not exactly sure I follow. So you're saying the relation between the variance of the first passage time
and the expected value. So it's a bit similar to this trade-off between accuracy and resolution I talked about, but somehow adapted to this specific region that you define, and when the system leaves that region, you will count this as a tick. Whether you think there will be a similar trade-off between those two quantities, accuracy and average time it takes to leave the region.
Yeah. No, so from playing around with a few models, there seems to always be, if it's always kind of the same type as the one you find in the processes you were mentioning, I'm not sure, but you do always find some kind of trade-off. Let me just say this. So, depending on the model, if this is, for example, a qubit, with a single jump channel, for instance, then you don't actually need any of this, right? Because then it's a renewal process, like Marco described in his talk, which means that the waiting times are statistically IID, and so you don't need this kind of framework, although you can use it anyway. If you have a renewal process with more than one jump operator, then you get a Markov chain, right? So you get this Markov property, and then in that case, you probably already get some kind of modifications to the standard result that you would expect. But the nice thing, I guess, is that this doesn't require renewal, right? Your quantum system here could be anything.
Cool. Thanks a lot for the talk.